All right, about your programming test number 1, we definitely already started grading and we are very busy doing that. And hopefully by Friday, I know it's a drop deadline, but hopefully everybody will stay. That should not be an option for anybody, right? So anyway, so we'll give you feedback and the result by Friday the latest. You mean the grading so far? I haven't checked with the TA. I might touch base with them either later tonight or maybe tomorrow morning. Yeah. Okay, well, if I can share anything, I'll share, but nothing at the moment. And for your lab number 3, okay, that one there is going to be about mutual exclusion. Yeah, mutex, a little bit like that, critical section, right? Sounds familiar. What you guys learned in the operating system. I think I can definitely draw some nice connection to it. And this one here is going to be quite lightweight, but I will still give you guys close to 2 weeks to do it. And then I'm still debating about what your programming test number 2 format should be like, but I'll confirm also. And for this one here, there will be some textual tutorial for you to follow. I'll give you guys the link, and then it's going to be more like a guided study for this lab. Just reproduce the example, and there will be some exercises for you to complete. And I think that'll be enough. I think the main thing is for you to get exposed to using the global and also the future operator. Okay, we'll see. I'll release the lab, hopefully by the class on Thursday, so I can talk briefly about it. Okay. All right, and then, one thing that's also very important, I even forgot to mention here, your written test number 2, right? If you look at the semester calendar, okay, let's look at that quickly. 4315, and then, yeah, it's going to be Tuesday, yes, that's correct. Okay, we're here on the 14th, and then it will be next Tuesday. Okay, we're going to do very similar to what we did last time. For today, I'm going to focus on some example in the first half, and then I'm going to introduce the until, weak until, and release operator, just a formal definition. They're a little bit tricky, but I will give you some guidance. And you guys can take 1 or 2 days before Thursday to digest a bit, and then on Thursday, we just do example to reinforce. And then next Tuesday, the format will be very similar to the first test. So nothing will be surprising. And I'll also give you guys some example questions just to help you get prepared. All right, and then for programming test 2, it's coming, almost like last week, and then we'll talk about it later when we get a little bit closer. One thing at a time. Okay. Alrighty, so let's now talk about some stuff. And to begin with, I would like to talk about how we can nest the operator in a slightly different way. So let me just open the slide. Sorry, somehow you get closed. There we go. All right, this is what we did last time. Okay, we talked about how you can do the FG nesting, and you guys asked me about what about we got GF? Would it mean something different or the same? The answer is different, but we're going to talk about it. And also, if you got some nesting implies another nesting, that's also something we talk about how you can formulate its meaning. That's also very important. We got something like this today too. Right, let's now take a look at this second pattern. Okay, this one here is, what does it really mean? Where we have a model satisfaction formula to say does S, any states, satisfies GF, and then phi, the formula. All right, and what we want to do is to do something we did earlier, since it's been a little while. Why don't we try to formulate its meaning very quickly? Okay. I do have some informal description over here, but why don't we just try to formulate this before we even think about what it really means intuitively? All right. Again, guys, I think the most important thing is if I give you something that looks to be creative in terms of the nesting, you guys should really know how to figure out the formal meaning, right? That's the most important message. But this one, let's do it quickly. Since we know it's about model satisfaction with respect to S, so the first level should be for every path pi. And exactly, we'll start with S. And then the second level is going to be the G. Yeah. Yeah, we can say for every I larger than or equal to 1. And then finally we can get F. So we know that there exists some J and j larger than or equal to I, and pi j satisfies phi. Right, hopefully you are now quite familiar with it. It's actually a very standard way of figuring out the meaning. Before we talk about the next two questions about how to prove and disprove, that's also very straightforward. I will write down also briefly for your notes. Can you guys think about, given this math, how do you convince yourself what it really means? Especially how it is different from if we got, rather than GF, but we got FG. How would you put in your words? Oh, go ahead, Ali. Yes. Exactly. That's actually pretty good, pretty spot on. Okay. So if you imagine that, so we say for every pi, okay, let me just use a different color. For every pi, let's say this is such a pi that's representative. So you have some states, have some states, have some states, have some states, and etc. We're basically saying for every I, so for every states over here, for every states, there is some later states, j, such that the phi is established. So maybe the later state could be here, the later state could be here, and etc. So it never ends, this pattern. So that basically means the phi is basically always true. Doesn't need to be at a consecutive states, but always it should be true. You cannot wait for indefinitely often for that to be true. Okay, I'll write it down. Phi should almost always true. Okay? Relative to any states. Relative to any states. You can't wait indefinitely before phi becomes true. You can't wait. Okay, I'll put it here. Indefinitely for phi to be true again. All right, so these two are really important. And now let me tell you the standard saying about the GF nesting. Okay? So people usually talk about this pattern here being very useful. We're saying that whenever you have this pattern, that means this formula here occurs infinitely often. Okay? Not always, but infinitely often. Okay? Infinitely often. All right? So that's something you have to know. Okay? The standard meaning. Patrick. Okay. So that means, let's say, for example, relative to this particular state, so this is more like an I over here, right? We fix some value I. And then, relative to this I, some future states, j, must have the phi being true. That's what I meant. You cannot wait for indefinitely until forever because before phi becomes true again. It's got to be within some certain limits. It's not exactly formal, I agree, but I'm just trying to maybe to help you a bit. To say, given a particular state I, there's got to be some future states at some point. Eventually, yes, exactly. Okay, go ahead.
This one's kind of natural language to describe this kind of breaks, so the math definition is the only way we can define it without ambiguity.
Yeah, exactly. I mean, so I would say to define temporal operator, very often maybe you still want to look at the math to see exactly what it means. And after the break, we're going to see how we define another 3 operator until we can tell and release. Without really seeing the actual math, it's actually very confusing about what it really means, especially around the boundary cases. Right? That's what we'll see. All right, that's good. And then let me just give you this one here. Oh, sorry. Okay, this part here is just about some more explanation. You guys can take a look. But this one here is not as neat as the infinitely often. So I would say the infinitely often is really the standard way of saying. If you want to say some property, it should be infinitely often holding. Then you should be using the nesting. And one more time, maybe I mentioned earlier, but it's good to emphasize. You really want to distinguish between infinitely often the case versus always the case. Now, can you say something about implication? Does one thing imply the other? Or they're simply equivalent? Okay, yeah, okay, I agree. Okay, let's say this is 1, this is 2. 3 implies 1, okay, very good. However, 1, not necessarily in general. Okay, they're not the same, exactly. Okay, let me just emphasize again visually. This one is saying that if I got this many states, which is infinite on the path, right? So here I'm saying that phi doesn't need to be true at every consecutive state, as long as within some limits, it's always become true, eventually. Then that's okay. On the other hand, for the second one, it's much stronger. If I got an infinite number of states over here, okay, let's say here, in that case, phi must be globally always true, continuously. If you miss any one of them, it's not the case anymore. Right? That's why it's so important to understand this, okay, to emphasize. Okay, let's go back. Right, how to prove and disprove. Well, how about this? For proof and disprove, of course, for proof, you still actually have to, number one, consider the path pattern of your state diagrams. Right? And then, for each path pattern, you have to see, can you argue that go ahead, yeah, before I write further.
Probably jumping ahead, but it seems like the disproving and proving for geo seems to be like difficult for both of them because you have to be exhaustive.
I would say disproving might be easier in this case.
It seems like you have to still exhaustively search for both of them.
No, actually no. Because in order, okay, let me talk about proving first and then we'll go to disproving. Because the disproving, you should always try to flip the for all into exist and for all into exist. We'll get there, okay? Let's still talk about proving. So now if I want to prove this here, I want to argue for each states on the pattern. And number 3, you want to find out for every states that's there, where is the future states that's going to satisfy phi? Okay? For each states, where is the future states that satisfies phi? Okay, so these are the 3 just general principles. Of course, we're going to see examples. Sometimes it might be easier. For example, if I get to Chidalu, so let's say that in the state diagram, if we find that every state already satisfies a particular predicate, in that case, no brainer. You can just say it should be true. Yeah, Chidalu, go ahead.
Understanding what this means. It's basically just saying that for every path starting from this state,
Yeah.
for each state, there's at least one other state in the future that's satisfied.
Exactly. And here, when we say for every state, the middle quantifier, that one is talking about every possible state on the path. Right? And for every possible state, there's always a future state that's going to satisfy phi. So that's why we say infinitely often. Yeah, that's the right way to interpret. And let's go back to disproving. Okay? For disproving, let's go one by one. How do we disprove universal? You want to say, give a witness. Absolutely. Give a witness path. And what's going to happen for that witness path? And we're going to do the second level for, okay, let me just give a name to the witness path so I can refer to it. Let's say it's simply just pi. Okay? And then, so how do we disprove universal? We got to give some witness as well, witness states. Give a witness states on pi. Let's say this witness state is called S. Let's say S prime, because we already have S over here. Let's not get confused. And then after that, we're going to say for this particular witness state, S prime, we're going to use it to disprove existential. For that, I'm going to use a star, star, star. Okay. You want to say relative to the witness state S prime on the witness path pi. Phi is, rather than having some future states that's going to make it true, it will never be true. Never true. Okay, let me say one more thing and then I'll take a question. Okay, you can think about this guy over here. You can simplify that slightly if you want to. You can think about relative to S prime. You can think about S prime over there. You can think about it's globally true, not the case phi. Okay, that's what you can think about. Because phi is never established, never ever. All right. Question, go ahead.
For the second question, the third point, do you mean for each path?
For each states, because we are already, so only the first consideration here is about the path, right? So we're going to consider every path pattern. And for each path pattern, we got to consider for every state. And for every state, we got to consider some relative future states. So these are the 3 steps.
Okay. The third one is for each state, where's the future state?
Yeah, where's the future state that will actually satisfy phi? That's basically this part here, right? So let's say if I choose a future state at index I, so where is the corresponding future state j relative to it that's going to establish the phi?
Okay.
That's what it means, okay? All right, guys, are we okay with this? 1, 2, 3. Okay, I take silence as yes. All right, you're fine. All right, not too bad. I think this one here, in some way, it's not too difficult to really prove and disprove when you see the example. So let's do example right away. All right. Let's now take a look. And for this example, I'll separate them into 2 parts. The second part got even a little bit more nesting and also implication. We'll do that maybe in the second part. Why don't we try these 2? Okay, this is again the diagram. Okay, and for our convenience, why don't we write down the path pattern anyway, since we keep talking about it. The path patterns. So what you really want to consider will be, for example, you might have S0, S1, S0, S1. Basically just this particular cycle. Okay? You might have number 2, S0, S2, and then after that you get stuck. Okay? This will be the second one. Okay, there's another one here. You can say number 3, you can say S0, S1, and then you don't go for any loop, you just go to S2 directly. Right? We actually talked about this numeration before. Right? That means you just go for another one. Okay? And then, very similar to number 3, you can say S0, and then S1, S0, S1 for as many times as you like, and then after that, you will go to S1 and then S2. Okay? It's basically, number 4 is like this. You can go for as many cycles as you like, and then you can go here. And after that, you get stuck. Okay. I believe there's another one. Okay, number 5. Okay, so here we have, we got 4, right? Good. Number 5. Okay, yep. S0, and then S1, and then S0, and then S2. And then you actually get stuck, right? Similarly. Yeah, these are very similar. Of course, if you're given a different example diagram, then you might have something different, okay? But just the principle. All right. So you rather hope the question you're given actually got the answer false. In that way, you just need to find a witness, okay? Yes? Absolutely, that's what I planned. So I think the exercise I'm going to release as a practice question. I'll give you a different diagram so we can try to practice on that. Yeah, for sure. Yep. All right, guys, given this sketch aside, how about the first one? Sometimes you may not want to just dive too much deeply into the pattern. You can look at the diagram and ask yourself, is it always the case that P is going to happen infinitely often? Ellie?
I believe you could go from 0 to S2 and then it'll never occur.
Yeah, that's obvious, right? Yes, absolutely. So I think in this case, it's actually false. Okay? Okay, it's going to be false for this one. And whenever you want to disprove it, you can definitely refer to what we said here, right? You have to give a witness, okay? I will give you a witness path, as Ellie said. So we're going to have S0, S2, and we just get stuck. You can see S0 itself satisfies P. However, starting from S2, P will never be satisfied again. So it's not infinitely often. All right? So that's false. All right, this one's easy. How about this one over here? Is it infinitely often the case that we satisfy either P or Q? So if you don't think that's the case, can you give me a witness? Yeah, we may use the same one, right? So let's say, for example, if I actually got to here, S0 to S2, and then keep going over here, and then I'm going to get P or Q simply unsatisfied. That one is also obvious. Okay, we can give another example. So you can also try, so this one is also false. And then for this one here, we can also say S0, S2, S2. The same witness path, which is okay. You can see in the beginning states, it does satisfy P or Q because P is satisfied. On the other hand, for all the future states, it is not the case, P or Q, because it only satisfies R. All right? And why don't we try another one? Okay, I'll put it here. What about S0 infinitely often, P or R? Sounds good, right? I can tell you that this one here is a special case. You don't even need to argue about the different patterns because every state over here satisfies P or R. Agree? Yeah. Okay. If I happen to give you a question like this, just answer. You just say every state involved in all the paths, they simply satisfy P or R. Okay? This one here is simply just true. That's awesome. Okay? Here you can say because all the states satisfy P or R. Okay? Let me just check. Yeah, so if you look at the slides, okay, I think in the slides I included this example here, but I did not include this one. Okay, that's why. Okay, so just a little bit more example on the iPad. Guys, are we okay? It's not too bad, right? Yes. Yeah, you can say that. Yeah, that's very good. Absolutely. Another way to really make a side notes, because S0, we know that is globally true, P or R, that definitely implies it would satisfy infinitely often, P or R. Yep. I heard but somewhere. Yes.
Sometimes it satisfies the first statement, but it doesn't satisfy the second statement, so you can't always use that method, right?
Okay, so if you know that your model already satisfies this, you can conclude it definitely will satisfy this. No, yes, you can. Yes, because according to here, if I know that for every state it satisfies the phi, of course, infinitely often it will satisfy. On the other hand, if I only know that infinitely often the formula is satisfied, it does not guarantee that you don't have any gap. You do have gap. Think about it. Okay?
Because if one is not satisfied, then how is the whole statement?
No, in this case, you can see this part here is satisfied because every state over here satisfies P or R. Right? Because this is satisfied, so we know that this one implies this one here. On the other hand, if somehow you prove this, let's say you show that, and the follow-up question could be, is this true or false? You don't know. It gotta depends on the cases. Not true in general, but on specific cases, having this true, this might be true as well. Okay. All right, that's awesome. Let's do one more, and then we can take a short break. Okay, one more. Okay, guys, look at the pattern here. All right. So I think this time I deliberately not try to do these two patterns from scratch because I think it's now to really not spoon feeding you guys too much. So what you really want to know is how to figure out the meaning for this. But I'll give you a little bit hints before we actually get to it. Okay, only worry about this for now. Let's say you're given this on the exam. It's kind of like an implication you have never seen before, let's say. How do you figure out its meaning? Okay, I'm going to put this guy over here. I'm not going to write down exactly, but I'll sketch the pattern. So that's something you can take a look. And then we just try to solve this question a little bit more intuitively. Okay? If I want to formulate this one here, what will be the outermost quantification? Jora, go ahead. What should we do? For all paths, starting with S, right? Why don't we start with that? That one is for sure. So for every pi start with S. Okay, it simply corresponds to this. And we got some very big body over here. Let's say this part here is green. Oh, sorry, it's orange. This part here is pink. All right. One thing to note, since everything you're defining within here is under this pi, so the pi is going to be shared. So for the same path you're considering, if for that particular path, GFP is true, that implies for the same path, GFR is true. All right, let me write it down a bit, and then I will let you guys put down the precise meaning. Maybe you can do some exercise here. So here I'm going to say some for all, I, and then exist, J, okay, and then P. Pi, J, P. So this will be just for this part, okay? And then we're going to say this will imply, okay, another one. Here it will be, let's say for every, I'm going to put I, but now you should really tell. The two I's over here are not interfering. They are not the same, right? They're bound to different universal quantification. And then I, and then some constraint over here, okay? There exists some J, and then pi, J, R. That'll be the formal pattern you want to make sure you practice and make sure you got it right. Okay? I'm only leaving certain parts to be blank, but that part, those parts should be quite obvious. All right, can we now try to say, do a little bit more visual, and then we can go back to this example here. Let's say pi, right? Let's say this is a representative pi. For the same pi with infinite number of states, we're saying that if on this path, P is infinitely often true, that means for the same path, R is also infinitely often true. This is just some sketching, not necessarily have to be for those indices, right? For the same pi. And for every pi you consider, the I and j could be different, okay? Guys, are we okay about this analysis here? Okay. All right, let's go back to this particular guy here. Do you think this should be true or false? True? Okay. I think for this implication here, we can apply some strategy. We can only, the only way to really make this false is when you got this one true, but this one false, right? So why don't we say, let's just assume this is actually true. What are the paths that's going to make infinitely often P true? Only this guy here, right? And for that particular path, is it the case that infinitely often R true? Indeed, because it always get R for alternating states. So that's why it's true. Okay, I'll write it down. So here you can say, assume GFP, and this tells you the only path to consider is this guy here, okay? S0, S1, S0, dot, 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 okay? And then number two, in that path, GFR, right? Always you're gonna say alternating states in that path, R will always be true. Not always, but infinitely often true. That's important. All right, so the overall answer is true. So let's give you one more example. Hopefully I'm not making any mistake. What about S0, GFP? The same, but now I say GR. Is it true or false? Let's still do assuming the antecedents. By assuming the antecedents, we should really consider, again, this path over here. But now for this path, is it the case that R is always true? No. No, it's false, exactly. So this one, again, tells you that GFR and GR, they are different. Okay, hopefully that really makes sense. Okay, false. Okay. So now some justification. For S0, S1, dot, R is not continuously true. Okay, it's not. All right. Okay, that's all good. And let's now consider one more, and then we take a short break. False? Okay, if you think false, give me a witness path. Okay, actually, for this, if I give you exam question here, most likely the witness should be S0, S2, 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 most likely. Don't worry, I'm not going to give you the same one for the exam, right? I'm going to give you a new one. But for this one here, basically, you want to find a witness path, right? Thinking this way, if I have GFR infinitely true, in that way, it could be either this one here, right? Or it could be, also this one here. But since we want to find just a witness, right? So we can just say, let's choose this one here, where it is infinitely often R is true. But for this particular path, is P always true? Infinitely true? No, not really. Okay, so witness. All right, that's all good. So we have S0, S2, S2, dot, dot, dot. And then you can see that for this path over here, GFR is true. That was obvious because R over here. But the consequence, GFP is false. Because once you get to the S2, only R will be true. Okay, so that means you got true implies false, which is false. Okay, so the answer for this one here should be false. All right, we just did a little case study on the nesting. All right. All right, any questions? All right, if no, I would suggest we take a 2 minutes break, take attendance, and then we'll do until, we can tell, and release operator after the break. Okay? All right, let's now take attendance, and then you guys can take a break. Okay, let's now launch the course. How about this one here? All right, checking, please. Chidalu, are you checking? Okay, good. Too early, too early. All right, just in case you're not sure what you're doing, we're taking attendance now. All right, can I close it? I guess. Yeah, guys, don't go too far. We'll come back in 2 minutes. Okay. Mike, are you okay? Okay, just come on here. Are you sure? Okay, if you can do it now, that's okay. You know, I can save some. Okay. There we go. Okay, sounds good.
Questionnaire. I don't know why.
Did you push on the poll? You did, right?
Yeah.
What did it show to you?
It showed that the answer was correct. The answer was correct or whatever it was. I don't know.
Okay, so the attendance, you know what? I think attendance is the only thing that matters. If attendance will record it, it should be fine.
Well, I did click on it for today though. This is today's attendance.
Did it record the attendance?
It says it's absent for some reason. I don't know why.
I'm not too sure. You can sign the sheets if you want to.
Oh, wait, where's the sheet?
Grab a pen.
So just check mark?
Yeah, check mark and sign. Okay.
Is one of there or? Is it fine where it is?
Yeah. All right, guys, 1 minute. If we finish early, we let you go early today. All right, let's get started again, please. Okay. Yeah, the plan would be I want to introduce to you guys the last three temporal operators. And once we have gone through them, you will be ready to do the last set of exercises for LTL. And then after your written test number 2, we'll cover a new topic until the end of the semester. That'll be the plan. Yes? Program verification. Something about looping variance, something about weakest precondition, and you will also be able to do a little bit of exercise on the TLA plus to see how that can be put into model checking as well. Yeah, that'll be the plan. Yes. All right, so let's now talk about the 3 operators. And I would suggest for today, let's only try to introduce to you the operator, the semantics about the formal meaning using quantifier. And then I will raise certain important questions for you to think about. We can answer right away as well. And then I want you guys to maybe look into this formulation a little bit deeper before Thursday, and then we'll do example. Otherwise, if I present some of the example to you today, you may not appreciate that example too much. Okay, that'll be the plan. Okay, wouldn't take too long, but we'll see. If you guys got confusion, just let me know. The formulation is already on your slides, but I would suggest we try to build that from scratch. I think that'll be better for your understanding. Okay, let's talk about the first one. And if you look at the slides, right, so this is what we finished discussing before the break, okay? And now we have to go back to path satisfaction. We have been talking about model satisfaction by considering all the paths, but now let's talk about single path. When you first introduce a new operator to define, you want to define on a single path first, and then we talk about model satisfaction, okay? The first operator, okay, let me just go directly there. It's called until operator, just U, capital U. So this is a new operator. Okay? It's a binary operator. I'm pretty sure you know the syntax. That's what we did, right? When we first talked about this lecture. So this is called the until operator. You have some LTL formula, phi 1, as a first operand, or left operand. There's another formula as a right operand. All right, let's take a look. This is the meaning. Let's read it together, and then I will sketch this also a little bit here, and then I want you to take the formulation together and tell me if there's any boundary case differences. That can kind of show you just by having diagram and natural language description. May not be so precise even. Okay, that's something we'll see. So there is some future states satisfying phi 2. And until that moment where phi 2 is satisfied, all the states satisfy phi 1. Visually, something like this. If this is the path I'm considering, okay, I'm saying that somehow some future states, for example here, for example, Si. In this future states, I have, let's say, phi 2. Oh, sorry. Phi 2 over here. Okay. And then I'm saying until this point over here, I'm saying phi 1 should be satisfied. Something like until then. So that means right from the beginning until possibly here, I'm not too sure. The language was not really clear. Phi 1 should also be satisfied. This is more or less what's happening here. And this is kind of the best we can do by deriving the diagram based on the formal, the natural language. Guys, are you more or less okay? More or less, right? Okay, excuse me. Let's now take a look at the formulation, which is a bit complicated. Okay, let's now take a look. Okay, I'll build very carefully, and then we'll take a look together. So what we have is some path pi satisfies phi 1 until, or you can write u like this if you prefer, okay, until phi 2. Okay, if and only if. Okay, so we say that there is some future states. Let's do that part first. There exists, I agree, for sure. There exists some I. Okay, and then I larger than or equal to 1. And then, and of course, and let me get a little bit smaller. Okay, how about this? And then over here, we're saying that at that future states, phi 2 will be satisfied. That means pi I satisfies phi 2. Okay? And how do we formulate this part here? Until then, all the states satisfy phi 1. Do you think if I say I just put another until operator, would it work? But, well, that wouldn't work because it's infinite recursion. You don't even have a base case, right? So don't try this for another until operator. You cannot define something by itself without base case. Yeah, Patrick, go ahead.
For all j between 1 and I to the power of j satisfies phi 1.
Okay, let me write down what you said over here.
But is the until inclusive or exclusive?
That's the critical question.
I assume it's exclusive.
Okay, why don't I write down your version first, and then we'll go from there.
So for
Okay?
all j
Okay, for every j, I agree.
in, I guess, the range like
Okay, so here we can say, yeah, let's say 1 less than or equal to j,
less than I.
less than I or less than or equal to I.
Less than I.
Okay, so that means less than or equal to I minus 1. Okay, I just want to say I minus 1 more explicitly there. Okay?
I to the j satisfies phi 1.
Yeah, I would say that's a very good estimation. It's actually correct. But guys, I want to tell you that this formulation here, you want to pay attention to this boundary case over here. That's the critical bit. Okay? What does it really say? It says that, let me just try to fix the diagram a bit. Sorry, over here. Okay, let me fix it a bit. The correct way to do it would be, oops, that's fine. Okay, first of all, we got phi 2, and that should be satisfied at I. There's got to be some future state I. Let's say it's exactly here. Okay, so this is where phi 2 is actually satisfied. And then we're saying that phi 1 should be from here until over here. From 1 until I minus 1. Okay? From here until over here. So that would be phi 1. Okay? That's what the formula is asking for. However, there will be some critical question I want you to think just based on the formula, if that will be okay. Is it okay? Let's say this. Okay, I'll post two questions over here. Question number 1. Is it okay that phi 1 is always the case, but phi 2 is never the case? That's question number 1. Okay, I'll write down 2 questions, and then I will take some input. Okay, that's 1. Okay, I'll put another question. Is it okay that phi 1 is always the case. And we know that at some future point, phi 2 is the case. All right, these are the two critical questions. Okay, let me do one by one. I'm going to sketch a little bit on the diagram, right? Q1 and Q2. I want to, okay, I'll hear maybe any input. Yeah, go ahead.
Is it okay that phi 1 is never satisfied, but phi 2 is?
If phi 1 is never satisfied by phi 2, okay, that's something we can do too. Well, there are many possibilities, right? You can ask me a million of those, and we can never finish the class today. You know? Uh-huh. It doesn't need to be. It doesn't need to be. Huh? They could be the same. Yeah, phi 1 and phi 2. And I would say, how about we ignore the third question just for now, if you don't mind. That will actually give us endless loop. Jorah. That's something we can consider maybe later. But for now, let's focus on just these two. Okay. All right. So for question number 1, okay, if you say phi 2 is never satisfied, that's a problem. Because for the until operator, it is very important that the phi 2 should be eventually satisfied. So that's a must. Yes?
Why? So is that just by the definition of the until operator?
Yeah, exactly. Because for this n to be satisfied, this has to be true. This has to be true, but we're just making this false. Okay, good. So this guy here tells you it is not okay. Okay, not okay. However, this one here is actually okay. Because this one tells you that, yes, at some future point, indeed, phi 2 is going to be satisfied. More than that, not only that the phi 1 is going to be satisfied until this point, it's also going to be satisfied all the way onwards. Nothing is going to violate this one here. Okay? It's still going to be fine. So guys, I would suggest before we do some concrete example on Thursday, think about this formulation over here and think about the answer to these two questions. I think that will help a bit. Yes?
For the orange part, is the second not supposed to be implication?
Yes, I agree. Thank you. Absolutely.
From the dot means something.
Yes. Absolutely. Thank you. And I just noticed that for your, let me see. Yeah, I think for your slides, I also put some vertical bar there. That's not exactly consistent. I'll fix that. Okay, I'll fix that. But you can just go with this definition here. That's the right syntax. All right, that's until operator. Okay, remember the answer to question 1 and question 2. Now, we got the second operator, which is called weak until. Weak until in the sense that it is more tolerating. It will actually include the possibility of until, and it also allows another possibility. Okay. Weak until. All right. How do you write it? First of all, right? It's a weak until. W. Weak until operator. Okay. If there's ever a future state that satisfies phi 2, then until then all satisfy phi 1. This part here is exactly the same as what we wrote over here. Okay? Okay? However, I'll say otherwise, that means there's another possibility. Right? Phi 1 must be always the case. Right? This kind of tells you that the answer to one of the two questions I posed to you will be different for weak until. I will get there. Okay? So now let's talk about these two possibilities. Let's say this is possibility number 1, possibility number 2. Number 1 and also number 2. Number 1 is more like the until operator that we talk about. At some future states, phi 2. And then at least all the state before that should be satisfying phi 1. Phi 1 and phi 1. And of course, if you want to extend the truthfulness of phi 1 beyond this point, that's also fine. But at least, it should be at least until here. Okay? And what about the second possibility? This one here, otherwise, if you really cannot satisfy this, then phi 1 must be always the case. That means this phi 2 over here never get established. In that case, you must guarantee that phi 1 is always the case. Always the case. So phi 1, and also phi 1, and phi 1, and etc. All right? And now, how do we formulate this? We can tell. Well, you're allowed to really use the previous definition if you need to, right? Or, that sounds right to me. Okay, let's write it down. Okay, this one is not too bad, okay? Let's say we got phi 1, weak until, I'll just say W here, phi 2. If and only if. The first possibility would be, we simply say phi 1 until phi 2. I'm reusing exactly the definition from the previous page. Okay? But this is so-called weak until because it's more tolerating. It's not too strong. Okay? Or, I agree. Or what? Yes, but what about use quantification? Right? Or? Yeah, exactly. So for every, let's say, for some reason I use the quantifier k on the slides. I'll just be consistent. For every k larger than or equal to 1, and then pi k satisfies phi 1. That's the weak until. And Chidalu, go ahead. Either one. Okay, so yeah, in order for this one to be true, we can tell. Either the conventional until is true, or if phi 1 is always the case, phi 2 never gets true. It's just general or, just disjunction. So it could be this is true and this is true. That's okay. But it cannot be that this is false and this is false. It cannot be. Patrick.
I don't understand how this covers the case, or how this ensures that phi 2 does not occur in the future. Because the way I'm reading this is it's either the case that phi 1 until phi 2, or globally phi 1. Right?
But phi 2 may still be there. Yeah.
But in the verbal formulation, it says, if there's ever a future state, then this. Otherwise, phi 1. So is that otherwise with respect to the, if there's a future state, or is it with respect to the entire until?
Otherwise, don't think about it, it's more like a negation. That's not my intention. I'm more saying about there are two possible ways for this weak until to be true. Either that.
Otherwise makes it sound like the exclusive.
I know. It sounds good to me. Okay, maybe the wording need to be fixed a bit. Okay? Let me just say or. How about that?
Yeah.
Okay? Okay, I can see your concern. That one I agree. Good.
Still, it was exclusive form between those two because if it was the case that phi 1 continued to be true after.
I think that would be too complicated. I would say for this one here, think about either the conventional until will work. If that one doesn't work, check to see if it can be the case that phi 1 is always true.
Would it be wrong to say define the weak until as phi 1 until phi 2 or global phi 1?
Yeah.
Say that again.
Phi 1 until phi 2 or global phi 1?
Yeah, that would be okay. So what you're suggesting is, if I got this, well, because this one is really global, right? Yeah, that'll be okay. The text will somehow use a universal quantifications. That's why I'm just following that. But it will be okay if you say this. Until phi 2 or global phi 1. Yeah, that's okay. So this one here is either the conventional one or this one here, either way. All right? Yeah, we'll try to do some example, hopefully on Thursday, just to reinforce a little bit the understanding. Okay? And now let's go back to the two questions we asked before. This one here and this one over here. Okay, question number 1. Is it okay? Okay, I'll put it here again. Question number 1. Is it okay, I'll be precise, that G phi 1, but G not phi 2? This was considered as not acceptable for conventional until, but is it not okay for the weak until? Indeed, because it's covering exactly this case. Awesome. Good. Okay. This is okay because we got this. And for Q2, is it okay? Well, because it was actually okay by the conventional until already. That's already included. I'll just write it down anyway. Okay, and I'll take question. One moment. That G phi 1 and future phi 2. Absolutely, that's fine. Okay, good. Question. Weak in the sense that, okay, if you don't mind, I'm going to mention a little bit about 3342. Slightly, okay, if you don't mind. Unless you regret, ask me the question. That's okay, right? Okay, quickly, okay? Yeah, actually, that's just about 3342, but I did mention that in 3342. When you actually got two predicate P and Q in general, when you compare these two, if you somehow you can say P implies Q, if that's the case, you would say P is the stronger one, and Q is the weaker one. Okay? Implies. It should be implies. Because, okay, let me go a little bit further. Okay? So now if you try to see the satisfying values by the two predicate, and then satisfying values. The set of satisfying value X such that P of X would be a subset of the set of satisfying value for Q. And let's visualize it. If you think about the P here, and you think about the Q over here. So P here has less satisfying value. So it's stronger. Stronger in the sense that it will filter out more values. The conventional until. The U, that's correct. That's exactly right. Okay? So this is actually filters out more values. And the Q here, in some way, can accommodate more cases. Accommodates more cases. And let's now try to get back to our example here, weak until and until, right? So the P here is a little bit like, analogously, is more like the until. And the Q here is a little bit like the weak until. And what's the case that we can accommodate for weak until? It is when this is the case, right? And I like you guys actually to make it shorter. Guys, are you okay with this a little bit of digression? But I think that's important. Good. That'll be the best way to understand these two. And we'll do more example on Thursday. All right, final one. Okay, but we do have 10 minutes. But this one may not take too long. The third one is called a release operator. Okay, I can tell you that there is a formal relation between the release and the until operator, but that one I wouldn't want to get into it too much for today, or I will see, because that one is actually rather complicated. So maybe I'll try to get a little bit more prepared for that, and then I can guide you through a little bit later. But for now, let's just study that. Okay. How do we understand that informally? So this is called a release operator. Informally, we want to say somehow phi 2 might have been happening, and phi 1 is the one that's going to release the phi 2. Okay, I'll write it down first, and then we'll read the description. More or less, it's not exactly right, but phi 2 has been holding. And phi 1 releases it. Okay, not very precise, but that'll give you a little bit of intuition. Okay, so that's to say if there's ever a future state that satisfies phi 1, this is the time when you can actually release phi 2, because before that point, phi 2 is always satisfied. Before that point, okay? And I know you guys are very concerned about this word here, so let me just say or. Okay? Or another case to make it true would be phi 2, the one you want to release, is never released. That's why I say never released. Okay, let's see some visual maybe I'll take a question first. Go ahead. I would say they are somehow, I know, they're kind of very similar, but I would say try not to think about their formal relation. It's actually rather complicated. Okay, so thinking this way. When you say, let's say this one here, right? You're talking about phi 1 should somehow be true until phi 2 is true, informally. And this one here is saying that phi 1 is going to release phi 2 being true. It's like a dual, yes. But the dual relationship, to really specify that, is a bit complicated. Yeah, so I would say it would be quite a bit of a negation you have to study for. I would say let's not get there. That's too complicated for now. Jora, question.
Phi 2 is true, we want phi 1 to automatic or to 100% be false, whereas in the other one we don't really care.
Okay, well, that seems to be the interpretation from here, but let's see the formulation what tells you that. It seems like. Okay, let's take a look. All right, let's now try to do a little bit of diagram here. For the second case over here, right, we say that phi 2 must always be holding, right? So phi 2. I can think about phi 2 should always be holding. That means you got phi 2, phi 2, phi 2, phi 2. Okay? But question you want to ask yourself, for the formulation, does it really require, I know phi 2 should always be the case, but can phi 1 also be true at the same time? It seems like from the meaning over here, informally, phi 1 is not allowed to be happening over here, because phi 2 is supposed to release it, right? Yeah, you will see the formulation, right? That's something we'll dive a little bit deeper on Thursday. What about the first one? So there is some future state that's going to satisfy phi 1. Let's say this is the future states. Phi 1. And then, until then, we got phi 2. Okay? And phi 2, if we just do until, for example, it will only cover all the way until I minus 1, right? It turns out for release, you have to include this state as well. That's not exactly until, but by definition. That's why I put this overlay here. Okay, let's take a look at the formulation. I think that'll be enough today. So I would suggest you guys take a look at the formulation and the intuition, so when we do the example, you can appreciate a little bit more on Thursday. Okay, the final one. So here we would say the pi satisfies phi 1 releases phi 2. If and only if. And we're going to have an or. So let's do this one first. Okay? This one here, okay, the orange part is going to be for every k. K larger than or equal to 1. Yeah, G phi 2. That's fine too. I'll write it down too. And if you really like, that's what you can put on your notes. You can say G phi 2. That's okay. But one thing to note, in order to satisfy this, can it be okay? Let's say I have phi 2 all the way true, but I also got phi 1 true at some point. Yeah, right? As far as making this true is concerned, it's okay to have phi 1. It's not relevant to this one here. It only requires phi 2 to be true always. But can phi 1 also be true? Yes, indeed. Okay, let me make a note over here. this disjunction, this disjunct puts no constraint on phi 1 being satisfied. All right, so that's the second case. And let's now talk about the first case. And for the first case, I already told you the essence about it. You want to make sure this value over here should be included. All right, let's now do it. All right, for that one there is going to be, okay, this case over here. So we're going to do, there exists I larger than or equal to 1, and then let's say here, and then we're going to say pi I satisfies phi 1, right? That's exactly the phi 1 over here at state I. And, right, should be both, right? And then we want to say, for every j now will be less than or equal to I. You can notice one thing here. Less than, I'll highlight it, less than or equal to I. Versus, if you go back a few pages ago, here we say less than or equal to I minus 1. So they are not the same. All right, notice that. Okay. These are the bits and pieces you have to really watch out for. Okay. And then, so after this, we're going to say pi j satisfies phi 2. Boom. All right. So guys, any question about this, about the formulation? Question?
So to clarify, once phi 1 holds, every factors cannot satisfy phi 2.
Once phi 1 holds, it doesn't say that. So here you can see phi 1 at some future point it should really hold, right? Oh, you know what? I said something wrong here. Sorry, I beg your pardon. So that's confusing. This should be phi 2. I'm sorry. Beg your pardon. Okay, so can you say the question again? And then we'll use a diagram. Okay, let's say phi 1 at some point holds. Should phi 2 doesn't need to be holding or not holding. It can or it cannot. It may or may not. May or may not. It's not relevant. All right, so guys, what we're going to do on Thursday, and then I'll let you go. On Thursday, we're going to do some exercise to translate the English requirements into the LTL operator that we just learned today. And then we're going to do some conventional exercise on some state diagram. That's what we'll do. Okay, and then I'll speak about your programming, I'll speak about your written test number 2 as well. All right, take care, and then I'll see you soon.